All right, let's wrap it up in about 10 seconds.
I just, no, you're good. That's like all I got. And then they have rings. Yeah.
Okay. So one thing that I asked was, what was the limiting contributor to your ability to name them? What was the hardest part? I have a suspicion about what was the hardest part. All of it. Yes. What else?
I had to like convert it all into like the line structure.
You had to take out of this, draw it in bond line, and then you could name it. So now you see it's better if you can take that nomenclature skill and expand it to all structures, not just the ones that we use the most, which is bond line, but if you know there's a way for you to name it by getting it into bond line, start there. And then at least you can feel confident in your answer. What else? How about just inability to read what these drawings are trying to tell us? Is it obvious how many carbons are here? Yeah, they're explicitly shown. And is it obvious to see how many carbons are here? A little bit. A lot are explicitly shown. And then we've got that bond line idea that at these vertexes, they're not really bends anymore, but they're kind of ends. I've got more carbons. What about this? Could you tell how many carbons were in this structure? This, I think, is the most challenging until you get used to it. So, Jamie, you said you did. How did you count the carbons here?
I mean, you're looking down a bond line.
Good. So this dot is a carbon. This circle is a carbon. That's 2 carbons. How many other carbons in the structure? CH2 and a CH3. So 4 total structure, 4 total carbons. All right. I heard a lot of you get the name for this one. What is the root? What's the longest carbon chain? Sorry? F. Ethyl has the suffix. That means it's part of a group, a substituent to a group. F is the root. What suffix goes with this compound? Ane. Alkyl halides don't change the suffix. So the only other functional group is alkane. So this will be ethane. How do I describe the location and the nature of those halogens? 1 tribromo. I'm sorry. 1 tribromo is not enough. There you go. 1, 1, 1. Tribromoethane. Do you know I never actually took you guys through that last page of the nomenclature worksheet where we went back and gave a systematic name to sorbitol and freon? But it was something like 1122 tetrachloro 1,2-difluoro ethane is freon, and hexane 1, 2, 3, 4, 5, 6 hexaol was sorbitol. So they had some kind of fun names. Cameron.
Why are we writing down 3 ones?
Because I don't want you to be confused. This could be 1,2,2-dibromo. Actually, that would be the wrong locant set. This could be 1,1,2,2-dibromo, or it could be 1,1,1-tripromo. Sorry, I got mixed up a little bit. If I had one of these bromines on the other carbon, then it would be 1,1,2-tribromoethane.
Oh, so it's 1, 1 for each of the bromines?
I've got 3 bromines. I should have 3 locants. That's the redundancy, right? And some of the redundancy gets absorbed, like when you have a higher priority functional group. The alcohol, of course, in a ring will be on position 1. But on a chain, the alcohol could be anywhere. So there are instances where the locant is assumed. But in this case, we can never assume any of them.
If there is only 1 bromine in the whole thing, you do just not have any locant.
In a small molecule like this, you could call it bromoethane. But you couldn't in a small molecule like bromopropane. Because now you need to decide, is it one bromopropane or two bromopropane? Those are not the same structure.
Is that CH3 not a methyl group?
It's not,
Why the flip?
because it's a part of the longest parent chain. There's only 2 carbons in that structure, so the longest chain is 2 carbons.
And so the hydrogens still just get ignored in the name.
They actually get named as part of F. And
Okay.
AIM.
Because they're connected to the biggest chain.
That's right. Yep. Russ, did you have a follow-up?
I was just on the, I forget what that one's called, with the 2 circles.
Newman projection.
How would you figure out what the parent chain is on that? You just kind of have to like think spatially in your mind?
So you could take Brent's approach, which is convert this into bond line. Last week, I talked to you guys about taking bond line with wedges and dashes out of the plane of the board and then putting them into the board for the Newman projection. We could do that vice versa. We could take these out of the Newman projection and then slide them into the plane of the board, and we'd get something like this. That would be its bond line structure, but I don't think you have to. How do you find the longest parent chain? Well, here's a carbon that connects to this circle, which is a carbon, which connects to this dot, because I'm looking down that carbon-carbon bond, which connects to this carbon. So my longest carbon chain in this molecule is a 4-carbon chain. If it was a much more complex structure, and you've got more than just CH2Br and CH3, but you've got a lot of other longer groups, yeah, then it can be a little bit more challenging. But that's not where I'll challenge you. This is a good entry level.
And I would imagine if you've got this super long parent chain, do they use Newman projector?
Yeah, you can, but you might say something at the bottom like C6H12, you know?
To show how deep you're looking.
They might just combine it all into one group so that it doesn't get cluttered and messy, yeah? Or they might give some of those abbreviations like BU for butyl, PE for pentyl, HE for hexyl, and then that way they just abbreviate what the rest of the structure looks like. So in this Newman projection, we've got 4 carbons. We just found them. And they're all connected in a chain, so the root should be butane. How will I describe the position of that bromine? It would either be 1 bromobutane or 4 bromobutane. Would you agree the way I numbered it would make it 4? And that would be a higher locant set. So the true name here should be 1 bromobutane. How would we name this compound? What's the root and suffix? What's the parent chain? Four carbons again, yeah. So butane. And what are the substituents coming off of this 4-carbon chain? 2 methyl groups, dimethyl. What'd you say? Some people might look at this and say, oh, that's a tert-butyl group. I've got 3 CH3s connected to a C. But if I call that a tert-butyl group, we run into the error we had last week where now my longest parent chain is 2 carbons. When my longest parent chain could be 4 carbons. So I've got a 4-carbon chain, 2 methyl groups coming off of what position? 2. 2 methyl groups means 2 locants, 2,2-dimethyl butane. So you guys are starting to see the way different perspectives on a molecule can still be interpreted with nomenclature, just need some different techniques.
So on that second one, you did it connected to the bromine, and the bromine connected to the CH2. Would it be a methylene?
This is a methylene.
The other one on the left.
This one?
Yeah.
Yeah.
It went to the bromine before the carbon.
You know, there's a really common reagent that recently got regulated by the EPA, and it's called dichloromethane. You can see why, dichloromethane, 1 carbon, 2 chlorines. But its common name is methylene chloride. Methylene indicating the CH2 group, just like this is a methylene. Just like that would be a methylene.
So if it bonded to the bromine first and the bromine bonded to the methylene, would you include methylene in the name? So it changes.
Well, the bonding actually wouldn't work. I think you're describing bromine bonded to two groups, and that would put a positive charge on bromine. But there is an instance where the longest parent chain, perhaps, is really long, and then I've got this little CH2Br. And I would actually name this substituent as a bromomethyl substituent, because it's a bromine substituted methyl substituent. Kind of like how we have these groups, isopropyl, but we called it 1-methyl-ethyl. So this is a systematic name. A common name would be calling it bromomethylene as a substituent. I wouldn't lean into it. But also, I don't know. I like to give you guys more common structures. There's not going to be a lot of branching. Not that it's much harder, just not as common. Hallie.
Why is the T capitalized in
That's a-
but not in the dimethyl?
Inconsistency in your professor. That's the only reason.
Okay.
Yeah.
Should they be uncapitalized?
It's a good question. It is a name, so if you're going to capitalize anything, it'd be best to capitalize the first letter. But it's not like a proper name, so you can abbreviate it, or you can write it with a lowercase letter. Really, the only thing that should never be capitalized, but it's not something I look for to take points off of, is like the S in sac-butyl and the T in tert-butyl. Those are always meant to be lowercase letters. But I think that's just IUPAC getting too cluttered with its rules. All right, so these conformations, primarily with Newman projections, they help us understand energy strains within a molecule. One of the most important premises here is that molecules can rotate around sigma bonds. There's an important clarification there, which is they cannot rotate around pi bonds, but they can rotate around sigma bonds. Let's take something easy, like ethane. So I've got an ethane molecule here. I'm actually going to have you guys pass this around while I put some information up on the board, because I want you to feel that rotation around the sigma bond. So let me demonstrate. This is your sigma bond. I mean, we can rotate around all of these sigma bonds to hydrogen, but this is your sigma bond. True or false? Molecules are always stagnant. They're rigid. Very false. Molecules move, molecules bend, molecules stretch. And a lot of that can be impacted by light. We're actually going to look in our next unit at how we can use light to make molecules move around. So this molecule, ethane, exists mostly as a gas. And as a gas, it's running into the walls, running into other gas molecules. And sometimes it's getting hit in such a way that it starts rotating around its sigma bond. Now, what would cause it to stop rotating? Or what might cause it to prefer one position after it stops rotating over another? Or, as it's rotating, what energy is it experiencing? If you guys have ever seen figure skaters that pull in close and then spread out wide, you know that they're experiencing their energy differently because they're pulling their momentum in tight, stretching it out. So molecules, similarly, will feel different energies at different parts of its rotation around the sigma bond. So pass that around however you can. And just look down the carbon-carbon bond, get a sight like your Newman projection, and then look at the different shapes that it takes on. The first conformation is going to give us our general term. This is the eclipsed conformation. a bond line perspective drawing on this would have this kind of zig-zig geometry, not the zigzag you're used to seeing with bond lines, but a zig-zag. And I'm gonna place my reference somewhere. Doesn't matter where it goes. I think last week I showed you guys referencing it from the left. So this week I want to show you referencing from the right. I've got that central carbon and a back carbon. I've had students in the past that say, if I take this dot and I fill it in really big, it makes me understand that I'm looking at the front carbon more. But I think you guys are getting an idea. When you really sight down that bond, the front carbon completely eclipses the back carbon. So we just need a way to demonstrate both carbons. This is the way we do it. All right, I'm gonna grab this hydrogen that's coming out, grab this hydrogen that's going back, and I'm gonna stick them into the plane of the board. That tells me I've got a hydrogen going straight up, and then these hydrogens coming down to the side. Now when you guys are spinning that molecule around, you'll notice that when it's in this eclipsed conformation, you actually can't see the hydrogens that are on the back carbon. They're perfectly eclipsed. So how do we draw it then? We're gonna have to do kind of something funky like what we did with the dot and the circle. We're gonna draw these eclipsed bonds just off to the side. H, H, H. Just barely offset so that we can still get the idea. Anybody not get it yet? Now this conformation is actually its highest energy conformation. When a molecule is rotating and you freeze frame at this instant, it's experiencing a lot of energy. And that energy comes from torsional strain. What dictates a central atom's molecular geometry? What dictates its electron geometry? Number of electron pairs or electron groups, which we remember a theory called VSEPR, valence shell electron pair repulsion. We said that it's the repulsion of these electron pairs that push themselves into an energetic minimum with this geometry. Torsional strain is what causes that VSEPR repulsion, or excuse me, no. Torsional strain is the same effect. It is electron pair repulsion. The reason we call it torsional strain is because it's a result of rotating. It's a result of this torsional angle, this rotational angle, which is why they call it torsional strain. I would rather they called it electron pair repulsion strain, something like that. But we can connect it. Do you guys know torsion? The word torsion in other contexts? Care to share?
I mean, there's medical times where a torsion is like twisting of anything, like whatever you're talking about, that gets torsion.
Yeah, he's talking about testicular torsion. And which is a great example. Testicular torsion is when the testicles get rotated around too much and you feel that pain from the rotation. Rotate around your signal bond, you're going to get your electron pairs eclipsed, and that's going to cause them to be those magnets that you felt on the first day of class, and that's going to get them to repel each other. That's an energetic maximum. So if it has the energy to continue rotating, it would prefer to get into our second conformation. This is usually where my Midwestern accent comes out. This is the staggered conformation. How do you guys say it? Staggered. Staggered. Right, I don't know. I always get tripped up. I've been here too long. But I say bag and flag and staggered. You can say staggered if you need to. All right, well, this is what the bond line structure will look like. Notice how we get back this zigzag. I have one hydrogen that's coming up, and then I've got one hydrogen that's going down. And if I take a perspective, again, I'll look at the perspective from the right to the left, draw my dot and my circle. Which way is this hydrogen pointing on my Newman projection? Straight down. And I can visualize that by grabbing this, pulling it out. These two hydrogens are up to the right and left, and this hydrogen is straight down. What about my groups on the back? The hydrogen here is straight up. Now, when we relate these two molecules, or these two conformations, there are places you'll see that refer to these as conformational isomers. Isomer there meaning identical units. Isomer, identical units that are different from each other only by their conformation, their arrangement in space relative to rotation around the sigma bond. And what do you notice about the staggered conformation? Is there torsional strain? None. Why? Because those electron pairs are perfectly offset from each other. They're not straight on. They're not repelling. They're staggered. Low energy. Now, there's math that you can bring in here. This is where a physical organic chemist really loves his job. The math that you can do is you can calculate at a given energy, for instance, the temperature that you have, you can calculate what percentage of your molecules in a sample exist in the eclipsed conformation and in the staggered conformation. And at lower energies, lower temperatures, a higher percentage exists staggered because it doesn't have enough energy to kind of put up with that eclipsed conformation, that electron repulsion. At higher temperatures, you start to give enough energy to overcome that electron repulsion. And you can sit there and sit with it better. Okay? Questions? Let's move on to something bigger than ethane. First, we'll look at butane, and we'll get some of the common names for it. So why don't you guys pass this around and do the same thing. Sorry. Gotcha. Rotate around that central sigma bond. You can see that rotating around any of the sigma bonds does something. But the one that we're going to be interested in is this one between carbons 2 and carbons 3 of the butane chain. These are the conformations of butane. They're going to give us some stereochemistry terminology. So remember we talked about regiochemistry. Is this carbon primary, secondary, tertiary, quaternary? Talks about how carbons are related to other carbons. Some of our regiochemistry terms will be anti, gauche, or just fully eclipsed. Let's start with the lowest energy conformation. This is the anti-conformation. It's actually the conformation that you get when you draw butane as a zigzag. This is the lowest energy conformation. It's also why we draw bond lines as zigzags. We are presenting a molecule at its lowest energy conformation. The Newman projection has hydrogens in these central spots, CH3s directly up and directly down. What it's telling us here is that the groups that are anti are these non-H groups. And I want to clarify, non-H doesn't mean it doesn't have H. Non-H means that it's not hydrogen. So methyl is not hydrogen. Bromine is not hydrogen. An alcohol, an OH group, is not hydrogen. So those would all be non-H groups, heteroatoms, functional groups, stuff like that. And their relationship to each other, their stereochemistry, is described as anti. They are directly across from each other on separate carbons.
So when we're looking at these, we're looking at hydrocarbons. So that would mean that by the book, they're nonpolar, right?
Yep.
But there's still enough force that there is repulsion.
Oh,
that's
absolutely.
causing the rotation.
I mean, remember, everything is magnets.
Right.
Electrons are magnets. Protons are magnets. So you get molecules, those are magnets. But their magnetic attraction with other molecules and their magnetic interactions within themselves are very different. A covalent bond, magnetic attraction, essentially.
Technically, it's still, even though it's small, we're still talking about small polarity that's causing these rotations.
Not necessarily the polarity,
Okay.
but the electrons themselves, which are repelling other electrons.
Okay.
It's the electrons that are this line. I'm not showing you the electrons, correct? We're assuming that the line represents the electrons. And it's the electrons, and what do those electrons look like? They show up in their orbitals. And so it's that orbital to orbital overlap, which is where the electrons are found, is creating a repulsive effect.
So in the two CH3s right there, we're not talking about the polarity of the methyl group.
Correct?
We're talking about there's a group of electrons here and a group of electrons here
Correct.
that want to oppose each other.
That's right. We're not talking about partial positive, partial positive. We're not talking about partial negative, partial negative. We're just talking about stuff made of electrons, stuff made of electrons. Absolutely. So this is the lowest energy conformation for butane. We might say that it has a somewhat similar energy of conformation to our staggered ethane. All right, before I show us our next conformation, anybody not get the molecule yet? Thank you. I want to take a step back to look at ethane. How would you describe what has happened from this eclipse to this staggered conformation? We've done a rotation. Which carbon has rotated? I would say the back one has actually stayed the same. The back one, the back carbon had hydrogens up and down to the sides. The back carbon has hydrogen up and down to the sides. The front carbon had hydrogen straight up, and now it's rotated so that it has a hydrogen straight down. And how much has that front carbon rotated? It's hard to say because I didn't mark the hydrogens. It might have rotated by 60 degrees. It might have rotated by 180 degrees. It's hard for me to know. It might have rotated by 270 degrees such that this hydrogen ended up all the way down here. I also don't know if it rotated clockwise or rotated counterclockwise. And did I need to rotate the front carbon in order to show the energy changing in the conformation? No. So there's a lot of different things that we can do here. We can show the front carbon rotating in the Newman projection. We can show the back carbon rotating. We can show the front carbon rotating clockwise or counterclockwise, back carbon clockwise or counterclockwise. Some of your homework problems on active are specific, and they say rotate the molecule clockwise, rotate the front carbon clockwise.
No, what was one of the back carbon?
Okay, so they'll do the back carbon. I may not be as consistent, but it doesn't matter. Would you agree? we are just showing the molecule taking up space differently, and there are a lot of correct ways that it can get there. So what I'm going to do for the next structure is I'm actually going to rotate the back carbon by 60 degrees, and I'll rotate it by 60 degrees in 2 different directions. So I'm going to draw 2 different Newman projections here. If I rotate from a staggered conformation by 60 degrees, I'm going to end up in an eclipsed conformation. I'm keeping my front carbon the same, so I'm going to draw in CH3 and H's. And I'm rotating my back carbon. So my back carbon no longer has a group coming straight down. It's actually going to be eclipsed with my front carbon. So I have to kind of draw them offset. If I rotate the back carbon clockwise, my CH3 ends up being here. If I rotate the back carbon counterclockwise, my CH3 ends up on the right. These 2 structures are unique from each other. If I can have the molecule back. Did you guys get all? Thank you. They're unique from each other because I'm either rotating the back carbon to the left or I'm rotating it to the right. So the methyl group is having a different interaction with a different hydrogen. Or maybe I can say the methyl group is having the same energy of interaction, but with different hydrogens. So these are 2 possibilities. And they're of equal energy, and they are higher than anti because they are eclipsed. But they're not our highest energy conformation. We're going to rotate one more time. In fact, I want to modify something. Sorry. Instead of gauche, I'm going to call this gauche eclipsed. I think I'm saying it wrong too. I think it's more pronounced gauche. Does anybody know French? Gauche, what I've heard from students in the past is that it means kind of like awkward. So imagine sitting next to somebody on the train. So gauche. Like you're just bumping up against them and it's really awkward. It's a good way to think about this. Then we can describe gauche staggered. So once again, I'm going to do another rotation of my back carbon. Will my conformations be staggered or eclipsed? Anti started staggered. One rotation gave me eclipsed. Next rotation, staggered. So I'm going to draw my lines from the back carbon offset. My front carbon hasn't changed yet. CH3 straight up. H's down to the sides. Where's the CH3? When the CH3 was rotating clockwise, now it's up here to the left. When the CH3 was rotating counterclockwise, now it's up here to the right. Once again, 2 different rotation pathways, which gives me 2 unique conformations, but equal energy being experienced by the molecule here. This molecule gauche eclipsed, I should have added this in. Sorry. This molecule experiences torsional strain. Would you agree? Why does it experience torsional strain? It's eclipsed. electron pairs are sitting in front of each other, like holding like ends of a magnet together. You're feeling that repulsion.
Did you say those two versions are equal energy? Both of the photons?
Correct.
How would that be true if the carbons or the CH3 groups are closer to each other?
They're not any closer to each other. This CH3 is not closer just because it's on this side of the line compared to this CH3 being on the other side of the line. Remember, we're limited. I can't actually show it eclipsed. I really can't. If I drew it truly eclipsed, I wouldn't be able to show the CH3. So this is one of those instances where I'm offsetting a little bit this way or a little bit this way. It's actually a very similar conversation when we had this discussion about which way does a wedge go, which way does a dash go. Neither. These are equivalent to each other because they should actually just be this, where you can't see the dashed group, but we can't do that. I'm glad you brought that up. These are not different from each other. We're just limited on how we can portray it.
Doesn't matter what side of the hydrogen you're writing it on. So like with the methyl group, could you write it? Could you just rotate it a little bit so it's...
Yep.
Okay,
Yeah, you could just as easily have drawn this line
right there.
right there,
And then just move all the other ones.
and it would be exactly the same. Yeah, you could move all the other ones. You wouldn't have to. I try to be consistent, but I mean, we're doing the best we can with the limited.
Because that's not how it's actually appearing. It's just
Exactly.
visual.
Yep. It's just a tool. So use your tool as best as possible.
So I'm guessing that there's probably not anything in between in terms of how you're going to visually represent it. There's not anything in between eclipsed versus torsional, because being able to discern.
I think you would agree that in reality, the molecule has an unlimited number of positions that it can take. But it's not meaningful for us to analyze an infinite number of degrees of rotation, right? Instead, we're going to look at those major contributors. We're going to look at positions where bonds are completely eclipsed. This causes the highest energy. And we'll look at bonds where they are exactly staggered. They bisect the group on the back. That's going to make it staggered. Those would be the two types. We could dig into, like, what if it's 10 degrees closer to this side than that side? But we won't. Which means that for you, you won't have to guess, am I looking at staggered, eclipsed, or something in between? No, it's always staggered or eclipsed. So if it's not this beautiful
Balance
6
clock.
Yep. Then it's eclipsed. So if it looks a little bit awkward, it's eclipsed. Great questions, guys. Does this molecule experience torsional strain in this conformation? No. Electron pairs are not eclipsed. Then tell me why this molecule sits at a higher energy, is less stable than this conformational isomer. Right. So what I'm going to do to visually draw this is I'm going to draw these kind of circles around my non-H groups. The relationship that we call this is our non-H groups. We call them gauche. Gauche eclipsed is where those non-H groups are not directly on top of each other, but not directly opposite each other. They're somewhere in between. They're a little bit awkward between on top and away from. They're somewhere in between. With gauche staggered, they're somewhere in between and staggered rather than eclipsed. This introduces a new type of strain. This type of strain is called steric strain. This is how I like to think of steric strain. Physical, competition for space. True or false? The nucleus makes up most of the size of an atom. False. What makes up most of the size of an atom? The electron cloud makes up most of the size of an atom. Sterics comes from the same word as stereo, gives us an idea of spatial arrangement. Steric strain is physical competition for space. It's when these groups start to fight for physical space. And what makes up physical space? The electron cloud. So this is actually just more electron repulsion, but it's not electron repulsion from eclipsed pairs. It's electron repulsion from groups that are nearby each other. So here's this gauche staggered conformation. And I think you guys can see that the two methyl groups could be closer, but now they're actually, because this molecule is not stagnant, now they're actually starting to run into each other. They're starting to compete for some of that space in the molecule. That causes more electron repulsion, twists the molecule around. Everything's magnets, everything. Torsional strain, electron pair repulsion, just like what you felt with those magnets. Gauche steric strain, you're starting to get the exact same thing. All right, let's do one more rotation. And this one we can call the fully eclipsed conformation. It doesn't matter which conformation I use to get here prior. Oops. These are going to be the same structure again. On my front carbon, CH3 up, H's down to the sides. Now on my back carbon, I keep rotating one more group, CH3 straight back. Does this compound in this conformation have torsional strain? It does. It has eclipsed electron pairs. What else does it have? Does it have more steric strain than the gauche staggered? Yeah, they're closer to each other, they're fighting more. So let's rank these conformational isomers then. On the right-hand side, we'll put the highest energy conformation. On the left-hand side, we'll put the lowest energy conformation. You guys know energy is conserved, right? So if a molecule is spinning and it's going through different energies while it's spinning, that means that energy is put into this electron repulsion. So energy from somewhere else must be taken. So maybe while it's spinning, it actually slows down during that energy repulsion, or it speeds up, or it's similar to an ice skater trying to pull themselves in and out. They're conserving energy, but they're just changing it. What would be the highest energy conformation? Nope. Fully eclipsed, yep. And for what reason? Because this has the most torsional strain and the most steric strain. Or sorry, it has the most strains. It has both torsional and steric. What's the lowest energy conformation? Anti. Because here, it has no torsional strain or steric strain. Now, I'd like you guys to try and make a guess at whether gauche staggered or gauche eclipsed is higher energy. Your pre-reading might already give you an answer here. Okay, I'm hearing both answers. So really the question comes down to, does steric strain cause more of an energetic difference, or does torsional strain cause more of an energetic difference? Fair question. The answer is torsional strain. Torsional strain is stronger. Torsional strain causes more of an energy difference. That means that my next highest here is my gauche eclipse. And my next lowest energy is gauche staggered. I'm sorry, my drawings really got away from me. I apologize. That looks really bad. I hope you guys have more space on your page than I have on the board. Because now I wanted to go in and add things like, this has torsional strain, but no sterics. And this has, I said that exactly backwards, didn't I? Has no torsional strain, does have steric strain. And this actually has torsional strain, but it has no steric strain. At least not steric strain like this or this. These types of steric strains, where things are gauche staggered or fully eclipsed, those come from those non-H groups. CH3 with H, the H is small enough, it's not fighting for space. We don't say that it has significant steric strain. I want you guys to take one thing away from this. There is actually a line. It's not a pretty line. What do you notice about all of the conformations on one side versus the other of that line? Yep. Eclipsed conformations are always higher energy. Staggered conformations are always lower energy. So part of your job is not to decide whether this staggered is higher than that eclipse and lower than that eclipse. It's to just group up staggered and eclipsed, and then look for changes in steric strain. Torsional strain is always going to make staggered more energetic. Man, I said that wrong. Torsional strain is always going to make eclipsed more energetic, less stable. The distinction then between all of my eclipsed conformations is just how much steric strain they have. And the difference between my staggered conformations is just how much steric strain they have. So torsional strain helps me differentiate eclipse from staggered. Steric strain helps me differentiate within those groups. Now, we could just keep building slowly, but I think I'd like to take a look at a bigger molecule, put some functional groups in there, and start to see how do the different conformations rank up against each other. So, we started the semester off with this molecule. I'd kind of like to, oh, no, actually it's not going to be a good one to go back to. Shoot, I wanted to go back to glycine, the amino acid. There actually is an amino acid we can look at, like 1,000 others. Let's take a different approach here. Based on some nomenclature that we learned last week, we know that this compound has a dimethyl group And we know that its suffix ends with "one" for the ketone, and it's 1, 2, 3, 4, 5, 6 carbons long. So this is 5,5-dimethyl 2-hexanone. But I want to look at its energies, the conformational energies, down this carbon-carbon bond. So let's draw it as we see it right now. I really need to put red away because she's dying. What's coming off of my front carbon? Here's my front carbon because this is my eyeball. So my perspective is starting from this direction. It didn't have to. I could have looked the other way. It's just going to flip it. Name one thing that's coming off. There's hydrogens coming off. Are they coming off up to the right and left or down to the right and left? They're coming up. They're wedged and dashed and they're pointing up. So in my Newman projection, they're coming straight up. And then I can confirm that this group is coming straight down. I can abbreviate that group. I'm not doing nomenclature right now. So I can abbreviate that as C, CH33, or I can abbreviate that as TBU, tert butyl. It's not its systematic name, but that is the group. It's a tert butyl group. Now, off of my other carbon, where are those hydrogens coming off? Am I in an eclipsed conformation or a staggered conformation? Yeah, I'm in a staggered conformation. It looks just like my anti-butane, zigzag. If I was looking at my fully eclipsed butane, this is my bond line structure. That's not zigzag, that's zigzag. Here I've got zigzag, which means I'm looking at a staggered conformation, probably its lowest energy conformation. The hydrogens here are physically coming down on the board, so they're going to come down on my Newman projection. And then how can I abbreviate that? There's a couple of different ways. I could just draw its structure. There's a carbonyl with a CH3 coming off. I could also abbreviate it as COCH3. The O in parentheses is there to remind us that it's only bonded to the carbon. So it's there to kind of emphasize that it's a carbonyl. But if you don't like that structure, then you just draw out the bond line structure, carbonyl. We could have done the same thing with TBU. We could have just drawn those three groups. Lowest energy conformation? Yeah. Now, what I would like you guys to do is draw three other conformations. One of them that is gauche eclipsed, one of them that is gauche staggered, and one that is fully eclipsed for this compound. And go ahead and work on it with your classmates. Feel free to bounce ideas off of one another. We're going to do the same thing where this compound actually has two identical conformations that are gauche eclipsed and two identical that are gauche staggered. So I just want one of each type remaining. Here's a good, yeah, we've got one. We've got the anti-conformation. So here's a good place to start. Draw an eclipsed conformation and then fill it in. Draw a staggered conformation, fill it in. Draw another eclipsed conformation. You guys were pointing this out before. I did it a little bit different, a little less consistent. This time I kept these two lines on the inside. There's no wrong or right way. It's just about being clear when you do it. but you know you've got 3 other ones to fill in, start by just drawing those templates. And then come back in and decide, do you want to rotate the front carbon? Do you want to rotate the back carbon? And if you decide you want to rotate one carbon and not the other, start by just filling in the carbon that's not rotating. Its groups will stay in the same positions each time. And then all you have to do is move the groups on the other carbon one by one. Mm-hmm. Good. So you kind of see you rotated the back left, and then you rotated it to the right. Doesn't matter though, because if it was here, it would have been the exact same energy. Yeah, looks good. I think that if this was staggered, your lines can be a little bit more symmetric. It actually looks like you're trying to draw them eclipsed. It looks like you're drawing them just a little bit offset. So having them just like this would be perfect. Mm-hmm. Yeah, good job using different colors to kind of pull out the detail. Mm-hmm. Good work. Yes, you're off to the right start. Mm-hmm. It could totally be. Yes. When you're drawing a template of a Newman projection and then you're going to fill it in, you have a lot of options. So, yeah, actually, I see what I did. I started with my front carbon pointing straight down, and then all of my other groups, my front carbon was pointing straight up. And there is no reason it has to be that way. I think that was just an oversight on my part, or maybe force of habit. I'm just very used to drawing it like that. But you could just as easily, if that's what you want, to keep this front carbon stationary, yeah.
So it doesn't really.
It does not need to be drawn a specific way. There's a lot of freedom here with drawing it.
It seems like it would help to do that because you could just use that as your reference point.
Yeah.
Exactly.
Because that's kind of your anchor.
Yes, and that was my fault for having, for kind of drawing it differently. If I wanted to keep the front carbon the same, well, I'm just going to draw in my tert butyl group at each of those positions, and my hydrogens at the other positions. And I know I'm not going to change those, so I don't have to go through the work. And then I was going to have one more that was staggered and 2 more that were eclipsed. Now all I have to do is rotate my back carbon through the different conformations. So from this conformation to gauche eclipsed, I got my COCH3 group coming off to the sides. How does this compare in energy to my first one? Higher or lower? Higher because of? Name the strain. Torsional strain. If I rotate it one more time, then my carbonyl group actually comes down here. That's my gauche, because the non-hydrogen groups, the functional groups essentially, are adjacent to each other. And so I get this steric strain between tert-butyl and the ketone. How does that compare to gauche eclipse? Lower energy. How does it compare to anti? Higher energy. Because of increased steric strain, but decreased torsional strain. Great. I do one more rotation, and my carbonyl group is directly eclipsed with my tert-butyl. One thing I want to point out, I'm switching back and forth between bond line and condensed formula for two reasons. Both are acceptable, so you can move back and forth as you like. I feel like I was crammed for space here more, so I wanted to condense it. But also to remind you that if you don't like bond line and you think condensed form gives more information, that's totally acceptable. All right, so this actually ranks exactly the same.
So if I went like counterclockwise, is that the same also, or is that?
Absolutely.
Okay.
Yeah, so this ketone being over here would have been the same energy, and this ketone being over here would have been the same energy. And that's true for these molecules. That's not necessarily true for all molecules. So there's a couple of things that I want to show next. I want to look at this molecule in this conformation. And then I actually want to get this molecule into this conformation. And I want to find out what happens with my wedged and dashed bromines when I do that. So it might be useful to look at the Newman projections. Okay, I do have this force of habit of drawing my first, my front carbon with the group straight up. And if I do that, it actually means I'm limited on which way I'm looking at this molecule in particular. If I look at this molecule from the left, down this dotted line, then my methyl group would be coming straight down off of my front carbon, which means I am, by way of drawing this, looking at this from my right. Because now I have this methyl group pointing straight up. Where is this BR? Is it on down to the left or is it down to the right? I'm gonna do my little steering wheel. This feels like a boat wheel with those sticks coming out, and then I pull it out, push it in, to the left. You agree? Grab onto it, bromine's coming out. So bromine's to the left. What's to the right? Sorry? Not a methyl. A hydrogen. It's assumed. It's not explicitly shown, but it's the only thing that could be there. It's the dashed hydrogen. All right, I look at my back carbon. What am I going to do? Bromine's coming out, hydrogen's going back. I pull that out, I put it back. Bromine's on what side? It's on the left. Same as last time. Okay, here's something I want us to point out. Wedged groups are on the same side. Nice. Now I can actually have a shortcut. I don't really have to go through this arduous process of figuring out my Newman conformation, my Newman projection. I've got a zigzag. Oh, I'm going to have an anti-arrangement. Here's my, I'll just clarify my second CH3. Zigzag, anti-arrangement. Wedged bromines, they're on the same side. Either they're on the left or they're on the right. Okay, well, I want to get down to this. It might actually be easier for me to do this from my Newman projection. Has anything changed from the back carbon? No. The back carbon kind of stayed with this zig that it's got. So I'm going to bring my back carbon back down. Nothing's changing. Which means I can feel very confident that on this carbon that has not changed at all in space, its bromine is still wedged. Nothing has changed. I rotated the other carbon. Now my front carbon, because I'm trying to get a zig-zig, I'm trying to go to this fully eclipsed conformation, my front carbon needs to have groups that come off here, here, and here. Just slightly offset. Would be nice if they were eclipsed. What's going to be next to the CH3? The CH3. So that means that I've taken this front carbon, and whether I've rotated it clockwise or counterclockwise doesn't really matter. CH3 is now down here. Okay, well that means that the H, likewise, has moved the same amount. So if my CH3 is now lined up directly across, my H will be lined up next to the bromine. And my bromine will be lined up. Boy, it just gets really cluttered, doesn't it? My bromine gets lined up directly across from it, next to that hydrogen. What side is this bromine on now? Is it on the left? It's now on the right-hand side of the molecule, which means it's actually on the same side as this hydrogen, this dashed hydrogen. So when I draw this again, should my bromine be wedged or should my bromine be dashed? Bromine's going to be dashed now because it's, my Newman projection says it's on the same side as this dashed hydrogen, and groups that are on the same side have the same perspective drawing. Russ?
So is this, maybe I'm overthinking this, but would this eventually play into the cis-trans discussion, where if we're going from wedge to dash, we're going from cis to trans?
So cis-trans is used with alkenes in a very different context.
Okay.
Cis-trans is used with rings, which are locked. So on a ring, groups that are considered cis to each other can never be trans to each other.
Because of the pi bonds.
No, rings don't have pi bonds, but rings have limited rotation.
Okay.
So rings will not be able to spin around 360. Rings can go one way or the other, back and forth, but they can't do this continuous loop.
So because this is rotation around a sigma bond, cis-trans is not
Correct.
part of this conversation.
We would say that these look cis to each other and that these look trans to each other, but we're actually going to use other stereochemistry later in the semester called syn and anti to describe them on linear chains and cyclic chains. But we'll touch back on that when we get back to the ring. Okay, so that was kind of a cool exercise. This is what I wanted to show you. Is that if I rotate around a carbon and I specifically highlight, if I keep my attention on which carbon is changing from zigzag to zig-zig, you guys get what I'm saying by that, right? Then that carbon's stereochemistry, its wedge and its dash, is just going to flip. The bromine goes from wedged to dashed after the carbon has rotated through this conformational change. So that's kind of a cool thing that we can point out. Wedge to dash during this conformational rotation. And we can use the Newman projection to try and get us there. I rotated the front carbon, and that actually proved for me this new structure. Now, there is another thing that we could do here, which would be grabbing these groups, kind of like how we took them out of the board to the Newman projection. We could grab these groups and pull them back into the board. And that would help me confirm wedges and dashes. I'm grabbing bromine with my right hand, this back bromine with my left hand, and I'm pulling them out and into the board. So this bromine goes in. This bromine comes out. It might look silly if you're sitting there on the exam doing this, but do whatever you got to do to help connect the three-dimensional molecule that we're trying to represent on a two-dimensional board. Okay, questions so far? Cool. One of your jobs in this section is to be able to identify types of strains by drawing molecules and stuff like that in Newman projections, but also to be able to rank Newman projections by the strain that they have, which comes down to as much as identify stereo relationships in here. And that's actually something I want to compare between these two Newman projections. I want to look at the different types of strains they have quick. What types of strain are present in this top structure? There's steric strain. There's this methyl group here that is sterically strained with this bromine group. Those are both non-H groups, so they take up space gauche to each other. They create steric strain. Where else? The other methyl and bromine. So that's two sets of steric strain in this one conformation. Where else? In between the bromines. The bromines are non-H groups. So there are three sets of steric strains here. And not all steric strains are identical. Steric strain increases with group size, which is to say a methyl group has less steric strain than an ethyl group, has less steric strain than an isopropyl group, has less steric strain than a tert butyl group. There's a lot of other groups that we'll look at, like bromines and alcohols and chlorines, carbonyls. But I think the one that is most common here is tert butyl. Across all of the common groups that we're going to see, tert butyl is by far one of the highest strained group. Let's look at this conformation. What types of strain are present here? Torsional strain for sure. Every part of this molecule in this conformation has torsional strain. So immediately, we know that this conformation is higher in energy than our first conformation. Just by nature of being zigzag, it is not as low in energy as the zigzag. What else? Where is the steric? The methyl groups have steric strain with each other. Anything else? Not really. Because we're going to call steric strain non-H with non-H. So bromine with hydrogen, there's not really a fight for space. The proton is not big enough. Bromine with hydrogen, no fight for space. There could be another conformation, I think you guys would agree, if I rotated this back by 120 degrees, I could get bromine to eclipse with bromine. and that would cause a different type of torsional strain. I wouldn't make you guys guess whether bromine over bromine and methyl over methyl is a larger strain. Just want you to recognize that they both cause strain. Okay. Now we're ready to move on. Any questions? Do you guys know where to find a model kit if you need it? STEM Center has one that you can borrow while you're in the STEM Center. So if you need a modeling kit so that you can put some practice to all of this, I encourage you to go there. The chemistry club has some in the ACS room. Good to know. True or false, cyclohexane is a flat hexagon. Anything you'd like to change about what I said? Cyclohexane is a flat hexagon. What? It's false. How would you change it? Pear shaped. Yeah. It is a hexagon, right? It's a 6-membered ring. When we draw cyclohexane like this, we call it its top-down view. If you go to the Canvas homepage, scroll down to Sim Otter, change from point group to molecule type. Under organic, you'll find cyclohexane. Oh, there's a few cyclohexanes. Let's just start here. What do you see? Top-down view. I see cyclohexane as this flat chair. Now, there's some perspective I could add in here. I think you guys would agree that at each of these positions, I could draw in a wedged H and a dashed H. And I could do that at every position. And we already agreed it doesn't matter whether one H is going one way or the other. They're actually eclipsed. I should only be seeing the H on top. I'm only deviating them so that I can see both H's when I draw them. Does that seem true here, that you only see the H on top, and that we'd have to rotate it to the side to see the H on bottom? The H's actually look different. Look at these 3 positions. There's a hydrogen there that we're looking straight down onto. And then down here, these 3 other positions, there's a hydrogen that's hidden. So it may look flat, but if you take this molecule and rotate it to the side, this shape starts to appear. Those 3 hydrogens that were spheres that we were looking down on, they were pointing straight up at your point of view. And those 3 hydrogens that were on the bottom, the ones that seemed hidden by the carbon, they were coming straight down, away from your view. And then there were 6 other hydrogens. We couldn't really tell, but those 6 other hydrogens were pointing straight out. Oh, is this going to make me, oops. They were pointing straight out, and, sorry, you can't tell from this perspective, but they're not all pointing straight out in the same way. Look at this hydrogen that's pointing straight out, and this hydrogen that's pointing straight out. They're on opposite sides of the ring from each other, and what do you notice? One is angled down a little bit, and one is angled up a little bit. So we're going to describe, we're going to create terms to describe each of those positions. Axial are positions that come straight up or straight down. So then we'll call them up axial or down axial based on our perspective. All of the other groups are equatorial groups. And we'll also describe those as up equatorial, if they're angled a little bit up, or down equatorial, if they're angled a little bit down. And then we'll look at how when a cyclohexane goes between different conformations, those groups always stay up or always stay down, which is why we can't go from cis to trans on a ring. If it's cis, it's cis. If a group is up and another group is up, they'll always be described as up. But between conformations, those groups will move from being in equatorial positions to being in axial positions, back and forth. So let's start in a similar way by looking at the highest energy conformation of cyclohexane, which they actually have an example of. I guess technically it's not the highest energy, but it's the higher energy one that is more meaningful to us. This is called the boat conformation. You can see on the boat that when it's drawn out, it does kind of resemble a little sailboat. We're not going to do a lot of drawings with the boat, but it's not really hard. There is an assumed piece of perspective here. Which of these lines is closer to me, closer to you? The bottom line. It looks like this. The bottom line is the one that's meant to come towards you. That is never going to change. One way that you can try to emphasize that is by making that line kind of like a wedge. And it says, this is closer to you. It's bolded. But you won't always see that. What we have to agree is that the bottom is always closer. Now the boat conformation is similar, I'm going to say approximately equal to, an eclipsed conformation in a linear chain. And actually we can take a Newman projection to show some of that similarities. So what I'm going to do is take my molecule and I'm going to sight down these parallel lines. If you guys observe the screen, I'll orient my molecule in that way. I'm going to sight down these parallel lines. I don't think I'll be able to get it quite flat. Oh, there we go. Now what does that look like? It actually looks like two Newman projections. Here's a dot, here's a dot, here's a circle, here's a circle, and those Newman projections are connected by two of their groups. They're connected by a group on the front, they're connected by a group on the back. So here's how I start drawing my Newman projection for chairs. Two little eyeballs. On the front carbon, there's a CH2 that connects it to the other front carbon. And it's connected up. Then these front carbons, they fill in the rest of their spots with hydrogens. We've still got that little peace sign that we were looking at before. But the other positions, they're just hydrogens. And on the back carbon, they're eclipsed. And they're even eclipsed with another CH2 in the back. So what does this molecule experience? It experiences torsional strain and steric strain. It might be harder to see the steric strain because it's happening right here. If I turn this boat back on its side, you can see the steric strain a little bit better. These hydrogen groups, these CH2 groups, they're kind of meeting each other in the middle at the top of the molecule, fighting for strain. We're not going to look at the boat a lot for this reason. It's a highly energetic, sterically, torsionally strained conformation. Cyclohexanes don't sit here very often. Then we have the chair conformations. And there are actually 2 of them for every molecule. If we put that in perspective, butane had the anti-conformation, the anti-staggered conformation. It had 2 gauche staggered conformations. So that was like a total of 3 staggered conformations, not to mention all of its eclipse. But a chair is only going to have 2. And these chair conformations, these are essentially equivalent to the staggered conformations. So on this SimOtter website, I'm going to go back to cyclohexane chair. Actually, just real quickly, there is something called a half chair twist, or I guess, yeah, half chair and twist boat. These are other conformations along the way, but they are not as meaningful as boat and chair. So I'm going to take chair and I'm going to draw it on its side again, show it on its side. Now here's how we draw this. I'm going to try to give you guys this like 4-step process. Number 1, draw diagonal lines. Draw them offset from each other. Whichever line is on the bottom, have that one lag behind. And if you don't feel like they're offset enough, then just elongate them so that they feel more offset. Offset diagonal lines. Whichever side is pointing up, you're going to connect those diagonal lines with a down V. And whichever side is pointing down, you're going to connect those with an up V. So you'll know if your lines are offset enough by whether your V actually looks like a V or whether your V starts to look like a straight line. For instance, if I drew these not offset, then it's hard for me to draw that V. But when they are offset, whichever one is on the bottom is offset further behind, then it starts to look more like a V. Other things that improve this, if you're drawing them flat, horizontal, not diagonal, even if they are seemingly offset, then things are going to start to look a little bit awkward for you. What chair does that resemble? I don't know. I didn't name that. I want to show you guys that you can do this in 2 ways. Chair conformations can point in 2 directions. I drew my offset diagonal lines going up to the left. Now I'll draw my offset diagonal lines up and to the right. It looks nearly identical, and there's no meaningful difference between the 2. How do I connect this side? The down side. Down side connected with an up V. You guys know what I mean by saying an up V? It's like an upside down V. Upside is connected by a down V, or just a normal V. Yep. All right, now we don't have a lot of time left, so I'd like to point out some positions on the carbons. Carbons are broken into 2 types of groups, up carbons and down carbons. If you look at this 3-dimensional structure, and if you draw it true, or if you position it truly eclipsed with itself, you'll notice that there are 3 carbons, 1 here, and then 2 that are eclipsed, that are higher up than these 3 carbons, which are lower down. So we're going to refer to these as up carbons and down carbons. Here, an up carbon is easily recognized because it is a vertex that points up on the page. Up, up, up carbon, up vertex. And a down carbon, just as equally recognizable. We've got these down vertices. on those positions, we get different types of groups. You'll notice that all of the up carbons, they have a hydrogen that is pointed straight up on the molecule. So up carbons have what we call up axial positions, because you'll see that that position aligns with what is essentially the axis of the ring. And then they have these equatorial hydrogens. They sit around the equator of the molecule, and they point slightly down. So an up carbon has up axial groups, down equatorial groups. Let's just round this out by saying what a down carbon has.
Yeah, excellent.
Good. Down axial plus up equatorial. What we're doing right now is just finding a way to understand the structure, finding a way to communicate about its spatial arrangement. What type of carbon am I looking at? Because that actually helps me decide how the groups are arranged. After we take a look at one, well, this is cyclohexane. It's done. We could draw in the hydrogens, but it clutters things up. What we're going to do tomorrow is start to substitute cyclohexane. What if we have cyclohexanol? What if we have bromocyclohexane? What if we have 1,2-dibromocyclohexane? 1,3-dibromocyclohexane? What if we have 1,1-dibromo 2-tert-butyl cyclohexanes? What do the conformations look like? Which one's higher in energy? Which one is more stable? And what can we do to look at the stereochemistry of that molecule? All right, we're coming back to chairs tomorrow, and then moving into section 5 as soon as we're done. Have a good night, guys. See you tomorrow.
Thank you.